Two things today. So I'm going to open up the first one that we're going to be doing, and we're going to work on a little bit of this together. So we're going to be working on covalent bond drawing practice. We've done this. I mean, we did it first semester, so it's been a long time since we really focused on it. But we are going to work on this. So what I want you guys to do while we wait for the rest of our class is to work on this section right here. Try and get this section done while we're waiting for the rest of our class to join us. Because then we'll go through this section, make sure we remember what bonds need to be formed, and then we'll continue on from there. So go ahead and open this worksheet up from Canvas and go ahead and do this worksheet for this top section. So again, we're doing that top section. Right now, we're trying it on our own, and then we are going to go over that section and continue from there. Give you guys about another minute to go ahead and do that section. All right, ladies and gentlemen, so let's go ahead and start going through this top section. So how many bonds does carbon need to form in order to become stable? What number did we decide? Do we remember? All right, I heard a 2. Does everybody like 2? Does anybody like a different number? I heard a 4. So I have a 2 and a 4. Anybody have 2, 4, or any other number? All right, I got a 5. Anybody have any different numbers or like one of those numbers from before? A 2, a 4, or a 5? All right, so let's talk about this and let's refresh as to what it means to make a element stable. So what are we talking about when we're talking about making an element stable? What are we trying to talk about right there? If we're making something stable, what are we trying to make it have?
A full valence shell.
Perfect. We want a full valence shell. All right, and if we want a full valence shell, that means how many valence electrons do we want?
8.
8. Awesome. So we want 8 valence electrons. All right, how many does carbon have? We have 1, 2, 3, 4, 5, 6, 7, or 8. We're close. We're close on that 6. So let's look at our periodic table real quick, if I can find mine. There it is. Our wonderful periodic table. We're looking for carbon, which is over here. This wonderful thing right here. All right. So it's element number 6. But remember, our valence electrons are only the electrons in the outermost orbital. So if we're counting just the electrons in the outermost orbital, we're going to count 1, 2, 3, and then 4. So carbon has 4 valence electrons. And so if we were to draw carbon with its Lewis dot structures, what is that noise? We were to draw carbon with its Lewis dot structure, we're going to draw a C, and then we're going to put 4 valence electrons on it. So 1, 2, 3, 4. So how many open spots does carbon have to form bonds? It has those 4 spots because it wants to pair up all its unpaired valence electrons. So we have unpaired valence electrons. We have 1, 2, 3, and 4. So we are going to form up to 4 bonds to make carbon stable. So now oxygen. Oxygen has how many valence electrons? It has 6, awesome, which means how many bonds is it going to form if it has 6 valence electrons? It'll form 2, awesome, because we have oxygen, we go 1, 2, 3, 4, 5, and 6, which leaves its 2 unpaired valence electrons to form bonds. So oxygen would form 2 bonds to be stable. What about chlorine? How many bonds is it going to form to be stable? Just the 1, awesome, because it's got 7 valence electrons, which means it wants 1 paired up to make 8. What about nitrogen? 3, awesome, we got it now. What about hydrogen? All right, I heard a couple different numbers. We got to remember that hydrogen has that 1 valence electron. Got 1 valence electron, but remember hydrogen only needs 2 valence electrons to be stable because it's in that first row, which means it only needs to form 1 bond. But what about phosphorus? Three, awesome. And last but not least, fluorine. One, awesome. There we go. Are there any questions on any of the ones we've looked at up here? All right, I'm going to take that as a no. All right, so then if we take a look real quick, just a refresher, pretty much all of our other non-metals from here over, all of our non-metals besides those noble gases are going to follow the same trend as the top. So hydrogen wants 1, carbon wants 4, silicon would also want 4, nitrogen wants 5, 3 bonds, phosphorus wants 3 bonds, arsenic would follow the same path. Same with sulfur would follow oxygen, same with selenium and tellurium, and fluorine, chlorine, bromine, iodine, they all follow the same path as well. So they all want the same or similar to what is above them in those columns. So all of them aren't written out, but they do follow the same pattern, remembering that. All right, so now we're going to do one example problem together before I let you guys go ahead and work on your own, just so we can refresh our brains as to what's going on. So we are drawing covalent molecules and we're drawing long chains of molecules, which means that they're going to be a little bit more difficult to draw than just normal one to one, which means if we take a look, we have C3H8, which means that we're trying to draw out the carbon chain first. And when I say draw out the carbon chain first, let's first draw it as Lewis dot structures to draw out these bonds to make sure all our valence electrons get paired up. And then we're going to draw it as those lines instead of the circles. So the first thing we're going to do is draw out our C's, and we have 3 of them. And we're going to put all 3 of them in a line. All right, so we have all of our carbons in a line, and it just didn't make enough room. And we want to create a single bond between each of our carbons. All right, so we're going to create a single bond between each of our carbons. And that's the first step. Step number 2 says draw a single bond between each carbon and the hydrogens, remembering that each carbon can have a maximum of 4 bonds. So we have 8 hydrogens. So we're going to start over on each side, and we're going to pair up 8 hydrogens. All right. So we have 8 hydrogens, and we're going to make a single bond between each hydrogen and each carbon. And then we're going to look. We're going to do 2 things. We're going to identify if there are any other non-metals that we need to put on our carbon chain. So are there any other oxygens, nitrogens, chlorines, anything else? If there are, we need to make sure we're putting them on somewhere, usually on one of the 2 ends. So either on this carbon or this carbon. We're not usually putting them in the center unless we're told specifically they go there. Okay, so we're going to look at the ends first. Then if we have no other molecules to put on there, we have to just double check to see that our carbon has 4 bonds between each carbon, and our other elements have all of their bonds. So each one of these guys has 4, and all our hydrogens have 1, which means everything stays a single bond. Which means now all we need to do is redraw it where those circles in our valence electrons become lines. So we have 3 carbons in a chain. Each one has the hydrogens coming off of it. Do we have any questions on how we just drew that? All right, I want you to try number 1 on the problems below. Take 2 minutes, try number 1. We are going to go over number 1 together, and then I'm going to let you guys work on the 2 things you have left for today. Take 2 minutes, get number 1 done. All right. Did we figure out this one? All right, I saw a couple thumbs up. So let's go through this one just a little bit quicker this time. So we start with our 5 carbons. So I'm going to draw 5 carbons. Put our valence electrons on each. All right, we need to make a single bond between each of those carbons. So we share 2 electrons between each carbon. Then we have 10 hydrogens left. So if we put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we give each of those guys a pair. And we have no more elements to use, which means all the unpaired valence electrons need to be paired up with another element, which means these 2 guys that are unpaired up here and here are going to bond together, which means these 2 carbons are going to create a double bond. So we should have a double bond between 2 carbons, and then a single bond between the rest of them, and a single bond between each hydrogen. And yes, I am aware that we could have put that double bond anywhere, which means you could draw that one in 1, 2, 3, 4 different ways. So any of those 4 would have worked. So if you put the double bond here like this, you had your carbon chain like this, or you had your carbon chain like this, or even like this. And then your hydrogens on the rest of them, wherever they needed to go. All of those work. This is just one possibility for you to do so. All right. So all of those do work. And you just have to make sure you are following the right path. Whatever it may be, just make sure all of your bonds or all of your elements have their complete valence shell. So all of them have a total of 8 valence electrons by themselves, or that they are sharing. The other thing I do want to remind you is things such as oxygen. These guys right up here, these ones that are alone, we need to make sure those continue to stay on oxygen after we draw out those bonds. So make sure those lone pair of electrons are staying on those elements even after you draw them down here. So if you have lone pairs, they need to be on this drawing as well. That's just a reminder. You guys have 5 more problems to work on this worksheet. You do have one other thing, and this one is a little bit shorter. It is another ed puzzle, and your ed puzzle this time is going to be on thermochemistry, specifically specific heat, which is an equation that we're going to be working with on Friday. So make sure you are also working on this ed puzzle, getting it done, and make sure you are taking notes so you keep that with you as you go through it. So the ed puzzle, I believe, is about 7 minutes today. So it's a 7-minute video for you to watch, I believe. And it's about specific heat and what that means and how we use that in calculations to understand the change in temperature of reactions. Does anybody have any questions? All right. And you guys are good to go. If you want to stay to work on this stuff, you can. If you want to stay to work on specific heat, you can. If you have questions on anything, please let me know. Otherwise, have a wonderful rest of your day.